In this sixth study problem associated with shear and moment diagrams, we have a much simpler looking kind of structure. Just a cantilever beam. The fixed end is at the right. We have an applied couple at the left and a concentrated load in the middle. Right? And so sometimes you don't actually have to calculate the reactions to be able to get going. We can kind of just see what will happen here. Remember, the slope of the shear diagram is given to us by the intensity of the load. The load is equal to 0 in terms of the distributed load, so therefore we start off at 0 and we go over then 0 to where the point load is at. Right? The couple doesn't do anything directly to the shear diagram. And then we have the 40 Newton load that will take us immediately down to a shear of minus 40. Again, no distributed load, so the slope is 0. And then we're going to need to have a reaction that would be upwards to close us off back to 0. We'll look at reactions here in just a little bit. Right? And then the moment, well, we have a smiley face moment that we start off, so we go from 0 to 100, and then we have dm dx equals v. Slope of the moment diagram is given by the shear. The shear is 0, so we have a constant or pure bending moment section of the beam. Then the shear changes and becomes negative, so we end up with a negative slope. The change in moment is given to us by the area of the shear diagram, which is going to be minus 40 kilonewtons times 10 meters, or minus 400 kilonewton meter. And so 100 minus 400 would give us a net of 300 negative. And so bam, there we are there. And we need to have then a frowny face couple at the end that's going to get us back to 0. Let's check this out here by looking at the equilibrium here. Let's take the reaction over here at the left as downwards. Using our sign convention, we'll call this B sub y, and positive for our moment at B, that would be our reaction, using the internal sign convention to show those areas. And if we were to sum moments, then about what that point that I'm calling B, we would have a positive 100 minus 40 times 10, and then let's see, minus m sub b equals 0, and therefore m sub b would be equal to a minus 300 in kilonewton meter, or not kilonewtons, but rather newton meters. Got that wrong down here, didn't I? Right, and sure enough, that's what we got. That this has to go in the opposite direction, and a clockwise moment will cause a upwards positive discontinuity, and that's exactly what we ended up with. So that's good, and of course the equilibrium here from the sum of force in the y is obvious. 40 down, you got to have 40 going back up. It closes off correctly. So there you go for that sixth one. There's your shear and moment diagrams.